Our main focus today is going to be to revisit the periodic table and the periodicity, which looks at the trends and stuff, information you can get about elements based solely on their location. Usually there won't be direct questions on the AP asking like what family is fluorine in, but knowing it is often a stepping stone to answering a larger question. So let's see if we remember at least where the families live on the table. Again, people at home, you should have already got these slides out in front of you because you cannot see what I'm projecting. All right, so what are these? These turquoise numbers are the what numbers of the table?
Oxidation.
No.
Transition.
No.
Families.
They're groups. They are group numbers. All right.
That's the wrong number.
We don't call them family numbers or anything. Oh, it is. Dang it.
That's not my eye.
I hope no one's recording this. Okay.
Oh, there it is.
Stop. Boop-a-doo.
No, it's highlighter. Stop.
All right. So here's where you impress me because you remember all of these. So let's find out. Oh, I'm supposed to only go black in here. Crap. Group 1 is called the Alkali Metals. Hey, are the alkali metals reactive or unreactive compared to the others?
They're reactive.
They're incredibly reactive because remember, the closer an element is to its octet, 8 valence electrons or none, then the more reactive it is. And our elements here in group 1 are chilling with 1 valence electron. All right? What about group 2 elements? They're called the...
They're the alkaline metals.
if you're dyslexic, they are the alkaline earth metals. It's only me if he really is dyslexic. Then he tells on me. All right, the alkaline earth metals live there in group 2. All right, remember those guys are also reactive, just not as reactive as group 1. All right, they're hanging out there with 2 valence electrons, which is still really close to being at their octet. All right, what about these guys here in the middle? What do we call them? These are our transition metals. If you recall, transition metals are often metals that you're more familiar with because they're not very reactive. They will react. They're just less reactive than most of the other elements on the table. That's why a lot of you are wearing them on your body at this time. All right, and they're not reacting with all the chemicals in your skin unless the gold that you're wearing is absolutely fake. You know who you are. It's also the reason that cooking supplies are often used with transition metals or alloys of transition metals because, again, food full of chemicals, and the last thing you want to happen is a reaction to take place while the chef is chopping up your meal. 13 through 16 here are commonly referred to as main group elements.
Since when?
When was this?
I have
Did
it
we
in
do
my,
that?
I got my old journal back, so I have all
Oh, yeah, you.
But that's not my old journal.
Who has journals still?
my old
What about 17?
halogen.
Halogen.
The halogens. Where are they on our reactivity scale?
They react.
They are just as reactive as the alkali metals, which is incredibly reactive, because they're just as close to their octet. They're sitting there at 7 valence electrons, which they don't want to lose 1 electron, they want to gain 1 electron, but it's equidistance from the octet. And then the one that you're commonly best at, 18, is the
Noble gases.
noble gases. Can anybody remember the vocab word that describes the idea that they're not reactive?
Inert.
Inert. They are inert, meaning that they will not react. They already have their octet. We can make krypton and xenon do some cool stuff when it comes to an expanded octet, but we'll talk more about that later. Are there any questions on our general families?
No.
Anybody miss their family?
No.
I don't have one.
Aww.
I miss going away too, but we have this boyfriend, Ocean.
What happened to Wiggly?
Oh, well, first there was a car accident.
Was Yoshi driving? Okay.
No. I
Um,
didn't know yet.
now, another item that we need to be reminded of is the general trends that we can discover about elements when comparing them to one another based off of their location on the table. There was three main ones that we learned about, aside from general reactivity. Can anybody name one of the trends?
The closer it gets to the right side of it, it's more electronegative.
As you go right and
Atomic radius.
up,
Atomic radius, right?
electronegativity increases. All right, and realize that I am pointing the arrows in the direction of the increase. Electronegativity was an atom's tendency to gain electrons. An atom's tendency to gain electrons. So it makes sense that electronegativity would increase on this side of the table because these are the elements over this direction that have 7 valence electrons. So again, they're wanting to gain to get to their octet. You need to keep in mind that electronegativity ignores the noble gases because, of course, they're not electronegative. They don't want to gain electrons. Therefore, what is the most electronegative element on the table? Fluorine, because fluorine is as far right and up as you can go while ignoring the noble gases. I heard another trend.
Atomic radius.
Atomic radius. Atomic radius. Which direction does that increase?
Left and down.
Left and down.
Down.
Atomic radius took a general look at the size of atoms in comparison to each other. Therefore, as you get towards francium, the atoms are the largest. This is going to have some impact on some behaviors that we're going to look at of subatomic particles in a way that we didn't in pre-AP. So that will be an important trend, as are the others. What's the missing trend?
Ionization energy.
Ionization energy. All right. Ionization energy refers to the amount of energy it takes to remove an electron from an atom. The amount of energy it takes to remove an electron from an atom. And this trend goes the same direction as electronegativity. And that makes sense because electronegativity looks at how easy it is for an atom to gain an electron. And those would be the same elements that would require a lot of energy to remove an electron because they don't want you to remove their electrons over on this side of the table.
Noble gases included for this one?
No, because it's still talking about tendency of movement of electrons. How are we feeling about these memories?
Good.
Schoology, of course, is going to quiz you pretty well on remembering how the trends work. All right, let's change gears just a little bit and make sure that subatomic particles and the way that they're counted are still fresh in our mind. This should be very simple. I'd like to remind you that the atomic number of an element is equal to the amount of protons that the atom contains. The mass number is a combination of what particles? The neutrons and the protons. All right, protons and neutrons. Those are the two particles given credit for having mass. Electrons do have mass, but it's negligible, so tiny that it doesn't throw off our devices. So with that in mind, we want to remember how to count these in some different notations. So let's start off by looking at nuclear notation. So let's look at a sample of zirconium written like this. In hyphen notation, the bottom number is the atomic number, while the top is the mass. But you could simply just remember that the mass number must always be larger than the atomic number, since the mass number includes the atomic number in it, the proton count. So applying this idea to counting should be easy if we want to know the number of protons, neutrons, and electrons. Let's prove.
Glad I got on video.
Yeah.
What was in there?
Spilled my drink.
It's probably
Oh, it probably was big red.
big red, but it's not in the can.
Ah, you're right.
All right. Anyways, let's prove that these cards are random.
Blue red.
What a god.
Where's that picture of you holding your card?
Now, it's just water, but it was delicious infused water that I won't have for my later periods now. Anybody want a strawberry?
Yes.
Yeah.
Strawberry? That was so gross. I sucked that up the straw and I spit it back in as I drank. I was like, can I have another one? Okay, here we go. Let's go to cluster 6, seat 4, Aspen. How many protons do you see, Aspen?
40.
She says 40. Do you agree?
Yes.
I agree. All right, let's head on over to cluster 3, seat 5. Reagan, neutrons. What was that?
It's like 50 or something.
You have a calculator there. Don't you? Here, steal.
No.
52. Now, remember, our neutron count is essentially a subtraction problem. Mass minus atomic number would remove the protons from the mass number, leaving you with only the neutrons. You can pass out. Oh, here, let me see, Aspen. I'll do it so you don't want anybody. All right, let's head on over to cluster 1, seat 1. Do you have an electron count for me?
No.
She says no. Hey, what was true about the atoms on the periodic table unless otherwise noted?
The electron is the same as proton.
Yeah.
Because the atoms are
They're equal.
neutral. Way to go, chemists. Way to use big words. Yes, but you're correct. They're equal to one another because we want the pluses and the minuses to be the same. Oh, I'm so sad. Okay. The other very common notation that we run into removes one of the values because hyphen notation makes the assumption that you don't need the atomic number. It knows that the atomic number never changes. Therefore, the periodic table that you have access to would always give you the info that you need. Let's take a look at vanadium 52. Now, in hyphen notation, the singular value given is the mass number, so none of the calculations of subatomic particles changes at all. So if we got ready to do it again, so let's go talk to some peoples. Let's go to cluster 5, seat 3, Aspen. How many protons? I'm sorry? 23. She didn't get that information from the notation. She got it from the atomic number on the periodic table. Let's head over to cluster 1, seat 3. 1, 3, do you have a neutron count for me? 29 is correct. Again, that was subtraction. Guys, when you don't stop me and ask questions, I assume you know everything that's going on. So if anything is weird, please stop me. Before I pick this last one, I'm going to change vanadium slightly. I'm going to make this vanadium have a charge of positive 2. This vanadium has a charge of positive 2. Let's go to cluster 2, seat 3.
21.
He says that there will be 21 electrons. Do you agree? Yes, I agree.
Nice.
The only way that we could be cationic and be positive is if there are more of the pluses than the minuses. So in this case, 2 more to make it plus 2. Questions? I'd like you to take a moment now and look at our glance at vanadium and what was the other one that I did? Zirconium on your periodic table. I want you to find those 2 squares on the periodic table. Again, they're near one another. And then I want you to look at the masses that I used for my 2 examples of subatomic counting. What do you notice?
You rounded.
Not the most common.
I did not use the most common isotope. You'll notice that the mass that I used is not what those averages round to. I'd like to remind you what an isotope is. Remember, elements can exist in different species. Those species would differ by mass, but the only of the particles that you can change to keep the element the same element but have the mass alter are the neutrons. And this is what creates isotopes. An isotope is different species of the same element with different numbers of neutrons. For example, if we were to look at this vanadium species that we just analyzed and change him to his most common isotope, well, it wouldn't be vanadium 52, it would be vanadium 51. And what would that change about my subatomic counts? Just the neutrons. The neutrons would now become 28 because changing the mass to create an isotope will only alter the neutron count. So vanadium 51 and vanadium 52 are 2 isotopes of vanadium differing by 1 neutron, is a way to summarize. What if you did change the proton? What can you? It would change a bunch of stuff. What things would it change? It would change the element. All right, she used the word transmutation, which is the correct vocab word for changing the element. What else would change?
Electrons? Well,
No, I mean, it wouldn't automatically change the electrons, but it would change the
Yeah.
charge. All right, if the electrons stayed the same and you altered the amount of positive particles, the overall charge would change. I heard mass.
Yeah, because of
All right, the mass would be thrown off. You'll run into Schoology questions that will like to give you those fun arithmetics. If you have this species and you add 2 protons, remove 3 neutrons, and add 6 electrons, what will it turn into? So make sure that you have a foundation on what these particles can alter. Are there any questions on some of this periodic table stuff? All right, how are we doing on time? We're doing all right. All right, we're going to change gears a little bit and start to tiptoe towards nomenclature, which is tomorrow's focus, but it's such a big topic that I want to get some of it covered today. So if you are doing things in your notes to show those change in directions, we're moving towards nomenclature now. Wow, this is a sopping wet table. I'm not going to clean it up on camera. All right, so ionic and covalent, we're looking at it from a perspective of naming, not a perspective of characteristics for the most part. But there are some items that we want to revisit and remember. Can anybody tell me what 2 things are bonded in an ionic compound? a metal with a nonmetal. All right? And you can look at that through the fact that a metal is a cation, while a nonmetal is an anion. What do those words refer to? Yeah, remember there was a plus sign in the middle of the word meow ion. Uh-oh, they laughed at it again. So some basic vocab covered there. Covalents were different because it was two what's together? Two nonmetals. A nonmetal bonded with a nonmetal. And realizing these differences is essential in your naming because you need to know what you're looking at to know which naming rules to use. Now, I do want to point out that if you look at your AP periodic table, what does it not have that the table that you used at pre-AP used had? Okay, the names of the elements, but you know those.
Also, where this bottom piece goes. He doesn't have that number.
All right, it doesn't show you where the lanthanides and actinides originate, but you can find that numerically. It doesn't have the staircase. Your zigzag's gone. If you remember that zigzag separated metals from nonmetals, and the metalloid semiconductors lived on the line minus aluminum. So you've got to make a note of that because you'll want to know where that division lives.
There's some new elements too.
The world keeps changing. It's wonderful. Another thing I'd like to just point out, though, is aside from the identity of the elements, there was a way in which electrons were transferred in each of these bonds. Can anybody remember the hot words associated with the way that electrons made the bonds form per type of bond?
Heat.
Not heat. Electrons were shared in which type of bond? Y'all want sigma to be the answer so bad. That's hybridization. We'll do that later. All right. Yeah, it was here. Covalents share electrons. And what do ionics do? They donate. So just another thing to keep in mind as we start to look at the nomenclature of the two. How many of y'all wrote the oxidation states on your new periodic table when you got it? If you didn't, that should still be a habit that you're in. So let me remind you real quick where they live. Because for your ionic nomenclature, you're going to definitely want to know. So make sure that your periodic tables are always labeled with these predicted charges, as they come in handy in many instances. So with that said, first, I think I almost did something. I'd like to quickly remind you of some of the transition metals that have multiple charges. You're supposed to already be have them in your brain from your polyatomic list if you'll change the page. But to give you them at a glance, all right, you have this information on your polyatomic sheet, but this is kind of a quick way to look at it and realize that there are some trends, some mnemonics that you could use when comparing the locations of these transition charges to their location on the periodic table. These are essential to know, so you're going to want to make sure that you're working on these multiple charged metals. And keep in mind that that is not a division line, that's a this or this line. All right. What?
What did the camera one time?
What are you gonna do with it?
I mean,
I hate him.
thank you.
Is it perfect?
Yes, it's perfect.
Anyway. All right. So with that in mind, we're gonna dive into the easiest of the nomenclatures. Which type of compound was the easiest to name? No, that's an element. What type of compound?
Salt, water.
Oh my god, it's going to be such an exciting year. Can you change the page? All right, so let's take a look at covalent.
Oh, yeah. Practice.
If you remember, our non-metals bonded to non-metals had a very simple set of rules associated with just knowing these prefixes. Now again, if you are copying this down as it's coming up, you're doing it wrong. Go to Schoology, get the slides, have this information in front of you before I start teaching, please. Here's the prefixes for covalent that you need to know. If you remember, covalent was the type of bond that did not require a lowest ratio of elements, meaning that the subscripts could be large numbers without them having to be reduced. So you had some interesting elements that existed, or compounds rather. There was one little rule with covalent though that had to do with one of the prefixes. Does anybody remember what that is? It never starts with mono. All right, mono can be used in front of the second word, but we don't use mono in front of the first word. So let's practice. I'm going to write a few examples up here. You do your best to name them. You are working independently right now, please. You know, I'm going to roll the dice on this first question. I hope it ruined your day. All right, let's see how you did. Let's go to cluster 4, seat 3. 4-3. She said, I'm sorry, dicarbon. All right, she wants to kill carbon. Die. Pentanitride. Notice that she changed the suffix of the second word to "ide", as is the normal practice for pulling elements off the periodic table into compounds. All right. Di for 2, penta for 5. Any questions? All right. Let's go to cluster 6, seat 4, aspen. What'd you get for the second one?
Sulfur octachloride.
She said sulfur octachloride. Do y'all agree or disagree? Perfect. She did not put mono in front of the first word. All right. Let's go over to cluster 5, seat 3, Aspen. What did you get for the last one?
I don't know. It's not covalent, but so I know it's not like a standard answer. I just don't know what it would be. 'Cause it's ionic, right? I just don't know what it would be called otherwise. I just know it's not one of those.
So when it's ionic, as you're correct, because it's a metal with a non-metal, we just ignore the numbers. So what's the first element you see?
Lithium,
And what's the second element?
oxygen,
Try it, but fix that.
oxide,
If you wrote dilithium monoxide, realize that you've been duped. And you need to not let that happen elsewhere. The biggest mission that you have for nomenclature is to first figure out what type of compound you're looking at and then attack it by that naming system. All right, ionics, a metal with a non-metal, they don't use prefixes because their subscripts are assumed within their charges, as we'll start to tackle in a moment. Questions? We got here at 35, right? Sweet. Will you change the page? So, as we tiptoe towards ionic, I'd like to remind you that it's the one that has far more rules to obey. You've got to watch out for charges, for example. If you were with me last year, then you know that the whole idea of checking charges and crisscrossing is not an arbitrary practice. When I introduced it to you, we did an activity where we started with 2 atoms and their Lewis structure with their dots, and we had to make the octet happy. So we would move dots from one to the other, and when we ran out, we would introduce another atom with fresh valence. And then we would move those, and then suddenly we'd have nowhere to move the dots, so we would add another of the other atom. It would have fresh valence, and then we would start moving dots around, and there always came a point where everybody was happy, 8 or 0. The crisscrossing of charges does that for us without us having to track the movement of valence electrons, but that, of course, is what's happening in ionic because it's a donation of electrons to bond. Canceling out is also a big ionic thing. As I've already mentioned, the ionics are the ones that have to be reduced. You have to show the subscript ratio in the lowest possible ratio. So if you have a +2 and a -2, it becomes a +1 and -1. If you have a +4 and a -2, it becomes a +2 and a -1. So you've got to be prepared to reduce charges. Parentheses, of course, to protect polyatomics. And then what type of compounds use Roman numerals, or elements rather?
Transition metals.
You've got your transition metals with multiple charges that can't easily be deciphered just by their name because they exist in different species. So Roman numerals are there for them to tell on themselves. The other little blurb I have added there is don't write the charges in the final formula. There's always a guilty student somewhere in the room that they take a -3 and a +2, and when they turn them into subscripts, the charge is still there. Don't do that. All right. Keep in mind that compounds by nature are neutral unless otherwise denoted. So make sure charges are not existing there if they're not supposed to.
What are the 3 transition metals that are always assumed 1?
The 3 transition metals that don't use Roman numerals are zinc, cadmium, and silver. That's on your polyatomic sheet that they are like that already, but zinc and cadmium are always +2, while silver is always +1. Try to stump me on the video. Dylan, I see what you said. I'm just kidding. All right, I want to give you a few to try before we stop. These will be our last 3 examples of the day, and then we will pick up on ionic tomorrow. So let's see if you remember what you're doing. Independently translate those into formulas. let's take a look at your brain. Let's head over to cluster 3, seat 4. 3, 4. What did you get for the first one? I just need the formula. Li3N. I agree. She saw that lithium was plus. Hello. She saw that lithium was +1, and nitrogen, which is nitride is nitrogen, was -3. There was no reducing that needed to happen, so the 3 became lithium subscript, and the 1 became nitrogen subscript. Yeah?
Yeah.
Let's go over to cluster 1, seat 4. 1, 4, what did you get for the second one?
RAS.
He says he got RAS. Because he saw that radium was +2, sulfur was -2, a reduction took place, so he crossed +1 and -1. How many of y'all knew what hypochlorite was without getting your without finding it on your sheet? Ah, y'all are so bad. Okay. Let's go to cluster 3, seat 2. 3, 2. What did you get for the last one? Here, quit shuffling for a second. You've got time. Still got 4 minutes, guys. I got SR. CLO. All right, so careful. So I heard you say -1, which is the charge of hypochlorite, but just while you're saying the formula, be careful because, of course, you never want the charges to live there. What's the charge of strontium, everybody?
2.
+2. So here was when my parentheses come into play because remember, polyatomic ions, when they're crossed a number bigger than 1, need to be protected by parentheses so that you've got 2 hypochlorites, not 2 oxygens. So hypochlorite would have been put in parentheses there, and then the 2 that he was crossed would be delivered. We will pick up right here tomorrow. Y'all have a great day.